The cosmos is painfully vast. If advanced civilizations ever spread across the stars and birth galactic-spanning empires, they will have to deal with the formidable challenge of interstellar communication. Frustratingly, Einstein tells us that particles cannot be accelerated past the speed of light, since that would require infinite energy, thus placing an apparent speed limit on communication. To us, the speed of light might seem awesomely fast, but to the universe, it's pitifully slow. So slow that for a galactic-spanning empire, its communication lag times would be up to 100,000 years. Just think of the enormous changes that have happened to our own species on such a timescale. Back then, our ancestors hadn't even left the African continent yet, let alone developed agriculture, writing, or science. Think of the countless wars, revolutions, episodes of growth and collapse, diseases, famines, and socio-political transformation that have transpired in that time. Certainly, by human standards, it would seem fanciful to seriously maintain a coherent galactic empire when communication lag times greatly dwarf the churn timescale of civilization itself. Faster than light, or FTL, communication could clearly come to the rescue here, especially if it were answerable, which is to say, instantaneous. Now, even if ships and objects are physically constrained to move slower than the speed of light, just being able to communicate faster than light would be game-changing for such empires. And this technology would also benefit more primitive civilizations such as our own, reducing communication lag times across the globe between our spacecraft and perhaps eventually between Earth and our distant solar system outposts. Unfortunately, in relativity, the speed of light isn't just the speed of a photon, no, it truly represents the speed of causality. Because in relativity, one can't even agree about what a simultaneous moment even means. Whereas Newtonian physics embraced this standard absolute sense of time across the cosmos, Einstein dismantled that and showed that it all depends upon one's relative frame of reference. Consequently, breaking the speed of light isn't just an issue of not having enough energy, it actually fundamentally violates causality itself. For example, allowing one to receive messages before they were ever sent. If you want to see how these paradoxes arise in more detail, then you should check out our video on FTL causality violations that we made earlier. These kinds of grandfather paradoxes upend the logical foundation of physics and are generally rejected under the causality protection conjecture, famously posited by Stephen Hawking. This would seem like pretty bad news for our hopes of FTL communication then. But that statement of impossibility really just derives from the theory of relativity, and most physicists would agree, including Einstein, that any physical theory is really just an approximation to reality and is not a literal description of it. So if we temporarily throw relativity out of the window, which remember is our best description of the universe at the largest of scales, that leaves us with quantum mechanics, which is our best description of the universe at the smallest of scales. Despite the undeniable strangeness of quantum mechanics, many of us might put more stock in its predictions over those of relativity. After all, this is a theory which we exploit far more in an everyday sense, such as within the semiconductors of your phone or computer. Yet more, its predictions have been tested to absurd precision. For example, the anomalous magnetic dipole moment of the electron has been measured to 1 part in 100 billion, and it still lands right on top of the prediction from theory. To paraphrase physicist Roman Jacques, quantum mechanics is unreasonably effective. Another attraction of quantum mechanics is that it was conceived in the absence of relativity. Now, yes, you can marry relativity into the quantum world and get something like quantum field theory, but the fundamental ideas are not predicated upon relativity. And there's even more good news, because when one takes quantum mechanics and looks at it fairly naively, there appears to be a way of achieving FTL communication. and that is quantum entanglement. After our earlier video explaining why FTL breaks causality, many of you commented about quantum entanglement as an apparent workaround, so let's tackle this today. The concept of a quantum entanglement communicator, let's just call it QEC for short, has been popular in science fiction for years. For example, in books, the Three-Body Problem series makes use of such a system. In movies, you have Avatar, and in video games, you have Mass Effect.
What's this area of the ship?
This is the FTL communications room. In addition to interfacing with the FTL comm network, Normandy is fitted with a quantum entanglement communicator linked to the Elusive Man's office.
So let's explain why it is that many fictional depictions have adopted this as their possible FTL communication system, and what our current understanding of physics actually has to say about the feasibility of a QEC device. The primary fact that QEC proponents highlight is that the effects of entanglement have been clearly established to travel faster than the speed of light. Now, that statement on its own isn't quite the same thing as saying, therefore, FTL communication is allowed, but naively, it seems like indeed it should make it possible. But what even is quantum entanglement? Let's start with a quantum superposition first, a core feature of quantum theory. To begin, we can imagine a single particle that is isolated from any other. Let's consider a particular quantized property of that particle, let's say spin, which can be either up or down, until something interacts with the particle, which could be an observer making a measurement, for example. The quantum state of the particle's spin is not either up or down, as we might expect classically, but rather it is a superposition of the two states. The particle is almost like an equal blend of the two, expressed like this. If we go ahead and measure the particle's spin, then this superposition state collapses to a single state, in this case with a 50% probability of each outcome. Quantum theory forces us to accept the idea that the universe is intrinsically probabilistic like this, something that unsettles many when first encountered. Now, it's important to emphasize that prior to this collapse, it's not merely that we don't know the spin of the particle to 50-50 odds, it genuinely exists in a kind of 50-50 ghost-like overlap of the two. Erwin Schrödinger, who was one of the architects of quantum theory, famously illustrated an extreme consequence of this with his thought experiment of a cat trapped in a box that ends up being both dead and alive at once. Now, entanglement is really just a special case of a superposition, and one that involves two or more particles. But rather than being a generic superposition, it's a superposition of correlated measurement outcomes, such that the measurement of one particle is associated with a definite measurement outcome for the other. Whilst we can entangle many different properties of particles, the usual example of this involves spin, where two particles are created together such that the sum of their spins is 0. It's still a superposition, and hence neither particle actually has a definite spin value, but because the sum is 0, when one of them interacts with the outside world and chooses a specific spin, say up, then the other particle responds by collapsing to the opposite spin state, in this case, down. What's so bizarre is that this happens apparently instantaneously, even if we take these particles and separate them across vast distances. Collapsing the spin state of one of these particles immediately collapses the other. But really, it's more accurate to say that measuring the spin state of one of these particles collapses the state of the pair, because when it comes to entanglement, they're in this together. Einstein was disturbed by this feature, since it seemed to violate his theory, and he called it spooky action at a distance. He even got together with colleagues Podolsky and Rosen, and they wrote a paper claiming that quantum theory must be incomplete as a result of this, often dubbed the EPR paradox after their initials. But today, we know that this remarkable consequence of quantum theory appears robust, and the speed at which this action at a distance occurs has even been measured to be at least 10 1,000 times faster than the speed of light. It's this feature of quantum mechanics that a QEC device is typically imagined to exploit. Surely the fact that action at distance occurs instantaneously establishes that FTL communication is possible, right? Well, as always, the devil is in the details. Because how exactly is it that you propose to use this for communication? Let's say that we have our two entangled particles such that their total spin is 0, and we put one of them upon a spacecraft that we're going to call Bob that is sent to an exoplanet, and the other one is left back on the Earth at a control center that we'll call Alice. Once the spacecraft has studied the exoplanet, the idea is to use this entangled pair to let us know whether Bob thinks the planet is habitable or not, rather than having to wait many years for a light speed signal to reach us. But here's the question. What exactly is Bob supposed to do in order to send Alice information of a success? Because the truth is that all we can ever do with such particles is open the box and interact with them, thus collapsing their wave function, their uncertainty. So if Bob does that, then the particle collapses and chooses to be a certain spin. 50% of the time, that spin will be up, and 50% of the time, it will be down. Crucially, Bob has no say or influence on that whatsoever. As we said before, quantum theory dictates that the universe is intrinsically probabilistic. This means that when Alice looks at their particle at the expected time, it will either be up or down with 50-50 odds too. Now, whilst it's true that Alice's particle is in the opposite state of Bob's, Alice actually has no way of knowing that, at least not yet. Bob could send a conventional radio signal saying what spin it saw, but then that's just light speed communication. In short, because Bob can't force an entangled particle to adopt a particular spin, there's no way to actually use this to transmit any information. It's at this point that your head is probably churning here, trying to think of some kind of workaround, and you're not alone. Many physicists have tried over the years. One simple idea is that Bob could take their particle and just keep measuring the spin state over and over and over again until they get the result that they want, thus forcing Alice's particle into the opposite of that desired state. However, this sadly also doesn't work, because the entanglement is lost the moment that you measure either particle's spin state. Like a one-time deal, it doesn't persist after that. This is one of the problems with the depiction in Mass Effect 2, which seems to present that entanglement of a single pair persists even after one measures the entanglement state, which is actually false.
I've never heard of a quantum entanglement communicator. How does it work?
Essentially, two subatomic particles are created in an entangled state. If we alter the state of our particle, that alters the state of the elusive man's. This allows us to send data in the form of quantum bits.
Okay, fine. Maybe you'll try and work around this by using a bunch of particles instead of one. So let's imagine here that Bob wants to get a spin-up result. So they open up the first particle, and if it's not in a spin-up state, they just keep going and going until they get the result they want. So let's imagine that after, say, 5 attempts, Bob gets a spin-up result. But again, consider what Alice sees. They have no idea that Bob stopped at 5, and so they will just keep reading off a sequence of random spins. And that statement is true whether Alice is the first to open the box or Bob is. Either way, Alice gets a random integer sequence and not a message. Okay, now some of you still might not have given up at this point and start thinking a little bit more deviously here, because surely there is some way we could exploit this for FTL communication, right? Well, usually when talking about this, there is someone who proposes the following solution. Maybe we just don't worry about the actual spin state of the particles. We grudgingly accept that the outcome will always be random. Instead, we denote a 1 to represent an entangled state and a 0 otherwise. The usual proposed setup here is that a bunch of particles are entangled and Alice is sending them through some kind of double slit type experiment. The solution here typically states that Alice should see an interference pattern whilst the particles are entangled, but that once Bob measures his bunch of particles, then the wave function collapses and Alice will instead start seeing 2 bright spots over each hole. If we're being technical here, then double slit experiments concern positions, not spins, but we could do something analogous for spins using a Rabi oscillation experiment. But look, that's not really the point. The real point of all of this is that Bob can choose whether or not to make their measurement. And so the instantaneous response as seen by Alice would constitute FTL communication. The problem with this proposal is that the premise is wrong. If 2 entangled particles are separated and only one of them is pushed through a double slit-like experiment, it will not produce an interference pattern. And that means that whether the pair remain entangled or not, Alice will always observe no interference, and hence no communication has transpired. Yes, you can get interference, but you would have to push both of the entangled particles through the double slits, not just one. To see why this wouldn't work, we need to better understand an interference experiment. In an interference experiment designed to identify a superposition state of a single particle, one first applies an operation to controllably vary the relative phase between the presumed 2 components of that superposition. So, for example, using a magnetic field if the superposition is between 2 spin states. Next, one performs an operation to join the 2 paths back together, here using a magnetic field in the perpendicular direction. And finally, one now measures if, after joining the paths, the particle is in a specific state, such as spin up. The superposition is identified by the oscillatory dependence of this probability on the imparted phase. If the superposition is in the joint state of the 2 particles, which is the case for an entangled pair, then the operation we need to do to join the 2 paths before performing a measurement must be a joint operation of those 2 particles. That is, we need to allow the 2 particles to interact in the interference apparatus in order to identify that they are in a joint superposition state. So either we'll have to bring the particles back together or use some long-range force like the Coulomb force, which of course we know cannot propagate faster than the speed of light. And so what this means is that in the end, Bob has no way to transmit information to Alice by measuring or not measuring their particle. Now, some of you might still be stubbornly clinging on to hope here, because after all, we just need to find some way, any way, that Bob can influence the state of their particle, and then the entanglement would cause that information to be transmitted FTL. So let's try one last idea, one that's a little bit more advanced. Remember that for a single particle, its spin exists in a kind of superposition prior to measurement. But really, the spin isn't just up or down, but rather pointing in some unknown vector in space. It could be in any direction, in fact. But when we measure it along some axis, let's say the y-axis, we force the particle to choose to be either up or down along that axis. However, we could equally choose to measure it along the x-axis instead, thus forcing the particle to be either up or down along that axis. Now, since that axis is drawn horizontally here, let's call those states right and left. So given this, perhaps some of you can see where we are going for our possible QEC device here. Alice and Bob pre-agree that if they observe their particles to be spinning in an X sense, so left and right, then that corresponds to a 0. But if they observe their particles to be spinning in a Y sense, so up and down, then that corresponds to a 1. Now Bob can choose whether to measure the spin along the X or Y axis. That's at the spacecraft's discretion. If Bob chooses X and measures, say, a left state, then Alice's particle will collapse into a right state instantaneously. Whereas if Bob chooses Y and then measures, say, an up state, then Alice's particle will collapse into a down state. That's Bob sending a 1. Sadly, this setup also doesn't work, and the more elaborate and complicated we make these schemes, then inevitably, the more nuanced the answer as to why they don't work is going to become. In this case, it really comes down to what Alice sees under these 2 possible scenarios. Of course, Alice doesn't know whether Bob chose X or Y beforehand, so Alice has to adopt one system of measurement as a default. Let's start with the easiest scenario where Bob measures a measurement in the same direction as Alice has chosen to measure in. Specifically, let's use the y-axis in this example. So that means that Bob measures in y, and 50% of the time will get an up, and 50% of the time will get a down. Now Alice is measuring in a y sense too, so they must see the opposite of whatever Bob gets, so that means 50% of the time down and 50% of the time up. So far this really isn't very useful. Alice is just getting a random sequence like before. But now let's consider the other scenario where Bob chooses to measure in the x direction instead. Now 50% of the time Bob will randomly measure a left and 50% of the time a right. So that means that Alice's particle must collapse into a left or right state. But remember that Alice has no way of in advance knowing that they should be making an x-based measurement. Instead, they are just sticking to making y-based measurements in our example. So then what does Alice actually observe? Well, this left and right spinning particle is essentially forced to make a choice between spinning up or spinning down. The situation is a bit like a coin spinning on its side. That's Bob forcing the particle into an x-basis sense when they make their measurement and collapse the wave function. But in this analogy, Alice can be thought of as pulling down on the coin with a force like gravity, forcing the coin to settle into an either heads up or down state. Which one emerges is a 50-50 random probability. So after all of this, we are left with the following result. If Bob measures in a y sense, then Alice, who remember is also measuring in a y sense, will see up or down to 50% probability. If instead Bob switches to an x sense measurement, then Alice, who is still using y, will see up or down to 50% probability. In other words, it makes no difference what Bob does to what Alice gets. Either way, Alice is left with a random sequence, just like we had before. After all of this, all of these ideas, tricks, and workarounds, we're basically left where we started. Because at the end of the day, Alice and Bob still have no way to communicate FTL. All their QEC device does, at least from their perspective, is just spit out a random sequence of zeros and ones. In a practical sense, the situation is really no different than some cosmic demon splitting up a pair of shoes, giving one to Alice and sending the other one to Bob in a concealed shoebox. Before Bob opens their box, the shoe could be left or right, with 50-50 odds. When Bob opens their box and sees a left-footed shoe, then by deduction, they know that Alice must have a right-footed shoe. But that's not communication. There's no way that Bob can somehow use that shoebox to send a message to Alice. There have been many different schemes proposed besides from the ones mentioned in this video, but all of them consistently fail to deliver an FTL system. In fact, physicists have even gone a step further and shown that if the fundamental assumptions of quantum mechanics are taken as true, then one can rigorously show that such communication is impossible, known as the no communication theorem. It really boils down to the fact that, as far as we know, one cannot influence the state which a wave function will collapse into. The universe appears intrinsically random, a god playing dice. And so because of this, Alice and Bob are doomed to only ever see random sequences. Despite this, quantum entanglement is still amazing and incredibly useful, forming the foundation behind quantum cryptography and quantum computing. In the next few decades, it could become an increasingly present part of our modern technologies. And when it comes to FTL, look, action at a distance genuinely does travel faster than the speed of light. So, does that fact in of itself establish that Einstein's speed limit is wrong, that his limit isn't some kind of fundamental law of nature? If so, that would at least give us some hope, right? It would at least crack the door open to some other possible FTL solution down the road. But sadly, even that's not true, because Einstein's speed limit isn't really about the speed of light, remember? it's really about causality. Relativity is actually quite content for things to travel faster than light. It's just that information can't do that. A good example is sweeping a laser spot across a distant plane from points A to B. You can make that spot move faster than the speed of light across the plane, but A can't somehow use this to send a message to B at superluminal speeds. And when we think in terms of causality, we see that action at a distance isn't in violation. It may be non-local, but it's not non-causal. What's so strange about this realization is that quantum mechanics and relativity are conceived from totally different starting points to describe vastly different scales. As I said earlier, there's no relativity built into the vanilla form of quantum mechanics. That's done through quantum field theory. But even with this simplified picture, we arrive at the result that the speed of causality is protected. When two vastly different theories, both supported by overwhelming observational evidence, arrive completely independently at the same conclusion, well, there is a sense that we are glimpsing some deeper truth here, that these are not mere curiosities or bugs of each theory, but rather a feature of the universe itself. Despite all of this, the story is not yet done. Theoretical physics continues to seek ever deeper descriptions of how the universe works, and surely one day we will uncover a deeper model that naturally unifies everything we know so far, and maybe even some new truths as well. Whether those new truths will provide the secret to FTL travel feels like wishing for a miracle. Sure, you can go ahead and hope it to be true, but none of us can claim that it's necessary or even likely. Perhaps part of maturing as a technological species is the acceptance that the universe appears committed, even dedicated, to ensuring slow speeds across its canvas. I know that this isn't the answer that you or I was hoping for. Trust me, I know. But just like with our own lives, praying for a miracle like winning the lottery or hoping that your problems will just magically disappear one day doesn't serve as a productive path to making future progress. At a certain point, you just have to accept the hand that you've been dealt and try to make the best of it. And often what can manifest from that is far more wonderful than you previously imagined. And so, I don't believe in miracles, but I do believe in our ability to make the best of our circumstances. So, until next time, stay thoughtful and stay curious. Thank you so much for watching, everybody. I hope you enjoyed this video. If you did, be sure to click the subscribe button down below. And if you really want to help us out, you can click the link up above where you can become a donor to my research team right here at Columbia University. Just like our latest two donors, I want to thank Nicholas Dahan and Ben Wolfred. Thank you so much for your support. All right, have a cosmically awesome day out there, guys.